In this example, the task will be to simplify the given complex numbers to a standard rectangular form, which will consist of a real number and an imaginary number, either added or subtracted. So for this first example, as you can see, the given complex number is cubed. And for this, we're going to use DeMoivre's theorem, which says that any complex number raised to the nth power, n being 0 and above, any integer, will be in this form. The modulus raised to the same nth power times the cosine of n theta plus I sine n theta. So using that, we know that 2 radical 2 will be the modulus of the complex number z, so therefore we have to also cube that, because the n in this case is equal to 3. That's the n value. And then we will get cosine of, now 3 is the n value, right? So it must be, we have to multiply 7 pi by 3, right? So it's going to be 21 pi over 4, okay, plus I sine of 21 pi over 4. And once again, I got 7 pi, multiplied the 3, and we got 21, right? Because the angle theta in this case is 7 pi over 4, and then the n value is 3. So 3 times 7 pi over 4 is 21 pi over 4. Okay, and the next thing that you're going to see is that we're going to have 16 radical 2. And how did I get that? Notice that 2 to the third is 8. Square root 2 cubed is going to give you 2 radical 2. 8 times 2 radical 2 is 16 radical 2. Okay? So, and then we will get what? We will have to evaluate this somehow, right? To make this the same position, we have to subtract a 2 pi or a multiple of 2 pi until there's an angle that we know how to evaluate the cosine at. Right? So notice that this is going to be, we can express this. So 2 pi and multiples of pi. 2 pi expressed as a fraction so that its denominator is 4 is going to be 8 pi over 4. Now 8 pi over 4 is not enough to subtract, because that's not going to lead us to the standard interval from 0 to 2 pi, right? We still need to subtract more than that. So we're going to seek a multiple of 8 pi over 4. And multiple of 8 pi over 4 is going to be 16 pi over 4, right? So if we subtract 16 pi over 4, we will be fine, because that would give us 5 pi over 4, and this is within the interval from 0 to 2 pi, right? We know how to evaluate that angle for the cosine. So now I sine the same thing, 21 pi minus 16 pi divided by 4. And that's going to give us what? That's going to give us 16 radical 2 times cosine of 5 pi over 4, right? We know how to evaluate that. Plus I sine 5 pi over 4. So now we know. So we know that cosine of 5 pi over 4 is exactly negative 1 over radical 2. Okay? And then plus I, we know sine of 5 pi over 4 is also going to be negative 1 over radical 2. So as a result, the radical 2's get cancelled out with both of these terms, because there's a radical 2 on the top. So as a result, we will have negative 16, and there's a minus for the 16, and there's an I, right? So it's minus 16i, right? So this will be the equivalent rectangular form when you cube the given complex number. So now let's confirm this result. Let's have fun a little bit with this. Let's confirm this result with actually using another formula, which is going to be a longer way of doing it, but let's see if we get the same result. We know when we multiply two complex numbers, we're essentially going to multiply the moduluses of the complex numbers, cosine of the first argument of the complex number, right, of z1, plus the second argument, plus I sine of the same two, right, the sum of the two arguments of respective first complex numbers and second complex numbers, right? So it's going to be this, right? So let's actually use that. Let's use that formula and see if we get the same result. So as you can see, we're going to use that formula twice, right? Because first we need to square, and then we're going to multiply it one more time to get the cubed. So let's see. So here's what's going to be. So we're going to get R1 times R2. So we're going to square that because that's the first modulus, and the second one is both of them the same, right? Because they're squared. So R1 times R2 is this thing squared. So that's going to be what? 2 times 2 is 4. 4 times 2 is 8. So we get 8. Okay, and then we get here cosine of 7 pi over 4 plus 7 pi over 4, right? Which is going to be 14 pi over 4, which is 7 pi over 2. 7 pi over 2. Okay, plus I sine of 7 pi over 2. Okay, and this will be multiplied by one more of this complex number, right, to make it cubed, right? So I'm talking about 2 radical 2 cosine of 7 pi over 4 plus I sine of 7 pi over 4. Okay. So now, let's see. So we're going to use the formula one more time. We're going to use this formula one more time. So as a result, this will be 16 radical 2, right? This will be treated as the first modulus, and this will be treated as the second one, the R2. So the product of these two will be 16 radical 2. As you can see, this already corresponds to 16 radical 2 that we found using DeMoivre's theorem, right? And we have to add these two angles, right? Like the formula suggests, right? So cosine of 7 pi over 2 plus 7 pi over 4. So that's 14 pi over 4 plus 7, 21 pi over 4. Okay? Plus I sine of the same thing, 21 pi over 4. Okay? So now notice that I'm not going to work any longer because we've actually arrived at this result. Okay, notice that this part is the same as this part, right? Because this thing cubed is giving you 16 radical 2, which is here, and the rest is being exactly the same. Cosine of 21 pi over 4 plus I sine 21 pi over 4. Right, so I'm not going to go any further. As you can see, it will lead to the same work. So there are two ways of doing this, right? The longer way is to use the individual product formula when there are two complex numbers being multiplied, and there's a shortcut when you're talking about three factors, okay, like 3 complex numbers, 4 complex numbers. But this DeMoivre's theorem actually works even when n is equal to 0, okay? Even when n is equal to 0, this thing still works, okay? So let's experiment. Let's actually think about what happens when n is equal to 0. If we plug this into the formula, let's see what we're going to get. We will get r to the 0 cosine. Now 0 times the theta times the argument is still 0, right? So cosine of 0 plus I sine of 0 should be 0. And that's equal to what? That's equal to 1. R to the 0 is 1. Now cosine of 0 is 1 and sine of 0 is 0, right? 0 times I is still 0. Okay, so as a result, this is 1 times 1, which is equal to 1. So that makes sense because z to the 0 power should be 1. Okay? And z to the first power will also work, okay? And okay, so now let's actually check out how this works, the division of two complex numbers. Notice that we can actually use the formula just like we used for the product. For the quotient, we know that this is equal to the quotient of their respective moduluses of these two complex numbers, and this is going to be cosine of the first argument minus the second one plus I sine of the first argument minus the second one, all right? And that would be the formula that we're going to use. So as a result, R1 divided by R2, the quotient of their respective moduluses is 4, right? So this is going to be 4. Now we're going to have cosine of the first argument minus the second one, right? So 3 pi over 2 minus 5 pi over 6, okay? And then plus I sine of the same difference, 3 pi over 2 minus 5 pi over 6. And what that gives us is, so let's see, cosine of what? So we need a 6 in here, right? So the LCD is 6, so that means 3 times 3 is 9 pi over 6. 9 pi over 6 is the same thing as 2 pi over 3, right? So this should be 2 pi over 3 plus I sine of 2 pi over 3, all right? So as a result, this is equal to what? Now cosine of 2 pi over 3 is going to be negative 1/2. And the sine of 2 pi over 3 is going to be radical 3 over 2. So as a result, this is equal to minus 2, right? 4 divided by 2 is negative 2. Now 4 divided by this 2 is also 2, right? So it's going to be equal to plus 2 radical 3i. So as you can see, we got another rectangular form representation of the given quotient of two complex numbers. So I hope this was useful. Thanks for watching, and I'll see you in the next video.